Now, when we learnt about polynomials, we learnt about multiple zeros, but we didn't yet have all the tools that we would need to find them quickly and easily. But now that we know how to differentiate, we're coming back to polynomials just for one lesson to have a look at how we can use differentiation to find those multiple zeros really quickly and easily. So first off, a little bit of revision. You have got this in your book already, but I'd recommend writing it down with the rest of today's notes so that it all comes together and makes sense. We've already learnt that the factor theorem looks like this. If we take some polynomial p of x, then if we've divided it by x minus something, let's say x minus alpha, then we'll get some sort of quotient. Now, we may also get a remainder. We've seen that. But what we're really looking at here, that's the remainder theorem. This is the factor theorem, which says if x minus alpha is a factor, then the remainder will be 0, won't it? So you'll really just get this and there won't be a remainder left. Now, what was q of x again? It's the quotient, isn't it? So it's just some polynomial in its own right, which is the factor, I suppose, that goes with this other factor. So when these two multiply together, you get the polynomial. So we can say that if we sub in some value of x, let's call it alpha, then if we get p of alpha equaling 0, then that happens because alpha minus alpha would be 0, and it turns this whole right-hand side to 0. So we saw that when that happens, we can say that alpha must be a 0 of the polynomial. And then x minus alpha must be a factor. So remember, we used our calculator hack to write down polynomials in their long form using that a button anywhere that was an x. And then we let a be different things. We'd try 1, -1, 2, -2. Try a bunch of small integers to see if we could get any of them equaling 0. And if they did, that one was a 0, and we had found ourselves one of the factors. We then used long division, remember, to find some of the other factors, and we looked at how you could use the sums and products of the zeros also to find other factors. Now, let's just revise our factor theorem a little bit to make it a little bit better. If we write it like this, now have a look at what the difference is between this one and that one. It's got that little m there, doesn't it? So that makes sense. We're talking about multiple zeros. If we have a 0 that's not just a single 0, but it's a double or a triple 0, and we saw that that affects the shape of the curve at that point, we can write it like this. Now, if we're writing it this way, that tells us that as soon as m can be a number, 1, 2, 3 or higher, then we can tell that q of x won't be divisible by x minus alpha anymore. Because if it was written this way, and we had, say, x minus, 2 as a double root, and it was actually x minus 2 squared, then it might be that if you just divided by x minus 2, then what was left over might also be divisible by x minus 2. But if we write it this way, it sort of takes care of that and ensures that q of x, or in other words, the other factor that goes with our multiple 0, and m could just be 1, won't be divisible by this factor. So this is the one that we should write down now and use today. Now, if q of x is not divisible by x minus alpha, then it stands to reason that the q of alpha won't equal 0. Okay, so in other words, just as when the p of alpha equals 0, we know that alpha must be a 0 of p of x. Well, if q of alpha isn't 0, then alpha can't be a 0 of q of x, and x minus alpha can't be one of the factors of q of x. Does that make sense? So let's just revise again what a multiple 0 actually does to the shape of a graph. We've got 4 polynomials here of increasing degrees. They're all what I'd call positive ones because the leading coefficient of x, if I expanded this out, would be positive. We've got one with the highest degree being 2, 3, 4, and 5, and I'm getting those numbers by imagining if I multiplied out the brackets, what would the highest power of x be? So I can see this is a parabola, a cubic curve, a quartic, and one with x to the power of 5. So that's going to affect the shape for sure. But they've all got the exact same x-intercepts. And remember, a 0 is an x-intercept. So I can go ahead and plot their x-intercepts straight up on my graphs. Now I've just got to put in roughly the right shape. So here I've got an upright parabola. It's going to look something like that. Okay, a bit of a dodgy drawing, but you get the idea. Here we've got a single 0 at x equals -1, and we've learnt that at single zeros the graph passes straight through, whereas at double zeros it just touches and then glances off again. So if it's an upright cubic curve, I know it goes from low to high. That means it needs to go through this one and then needs to turn around and just touch at that point there where x equals 2. For this one, again, it's going to go straight through the first one, but I know that a triple root has what I'd call a sort of wobble, a flat spot and a wobble, and we call this a horizontal point of inflection. Horizontal because it's a little flat spot, and point of inflection. So I know it's a quartic curve and it's an upright one, so it's going to go from high to high. So that means it needs to start high over here, go through this one. And when it goes through the two, it will sort of go through with a little wobble like there, right there, a little flat spot, which is a lot like the flat spot you'll get just on the simple graph y equals x cubed. This one is a polynomial with the highest power of x being x to the power of 5. So that means it goes from low to high because it's a positive one, and I need to go straight through this first 0. But when I go through this next 0, it's a 0 with multiplicity 4, and that basically makes it like a sort of like a parabola like this, but with a slightly fatter sort of bottom, I suppose. A fat bottomed parabola, I'd call it. Now, it's hard to tell on my graph whether it really is fatter than this one. For the purposes of our sketch, it doesn't matter. But what you'll see here is that if I kept on going with this, there's a pattern. For single zeros, the graph passes straight through. Once we've got a 0 with multiplicity of 2 or greater, it creates a little flat spot on the curve right at that x-intercept, or right at that 0. And if our multiplicity is even, then what we get is a horizontal turning point because it literally turns right there. So it's like a hump or a dip, I suppose you could think of it as. And if our multiplicity is 3 or greater and it's odd, so 3, 5, 7, 9, etc., what we get is this little wobbly section here, which is called a horizontal point of inflection. So let's write down something that summarizes all of that. A polynomial passes straight through zeros that just have a simple multiplicity of 1. But it will have a turning point at any 0 with even multiplicity, so 2, 4, 6, etc. And it will have a horizontal point of inflection, which is where we go up, do a wobble, and then go up again, or go down, do a wobble, and go down again, at any zeros that have odd multiplicity of at least 3. So basically, any 0 that's got multiplicity of 2 or greater, or in other words, is a multiple 0, has a little flat spot right at that x-intercept, right at that 0. And we've just learned how to find flat spots by differentiating and then letting the derivative equal 0. So that's exactly what we're going to do now.